problem. Hello, is it audible? Good evening. Is it audible? Okay. Okay, let us start today's class. Today is the last class for this linear algebra. Yesterday, after completion of solution of system of linear equations, already we have started the eigenvalues, eigenvectors, and we have written the definition of eigenvalue, eigenvector, and also we have written some note points, note point number 1 and 2. Next, continuation of this topic, note point number 3. Note point number 3 on. If A equal to 2 by 2 matrix with elements A, B, C, D, then the characteristic equation of A 2 by 2 matrix is lambda square minus A plus D into lambda plus determinant of A equal to 0. This is the direct formula to write the characteristic equation of any 2 by 2 matrix. Second order matrix characteristic equation is second order equation. This equation is contain three terms. Out of three terms, two terms are with lambda, one term is free from lambda. The last term is free from lambda. Second term quotient is, that is the quotient of lambda is trace of the matrix, sum of the diagonal elements. And the last term in the characteristic equation is determinant of A only. Actual method is we should write like this: determinant of A minus lambda I equal to 0, and you have to simplify this only. But after simplification, we get like this only. So just you have to remember this formula. Similarly, we write the same formula for third order matrix only. If A equal to 3 by 3 matrix, if A equal to 3 by 3 matrix with elements A11, A12, A13, A21, A22, A23, A31, A32, A33. Then the characteristic equation of A 3 by 3 matrix is lambda cube minus A11 plus A22 plus A33 into lambda square plus next term is lambda term. Its quotient is sum of the 3 second order determinants. Later we read the elements into lambda minus determinant of A equal to 0. The quotient of lambda square. The quotient of lambda square is trace of the matrix, that is sum of the diagonal elements only. Next, the coefficient of lambda is sum of the cofactors of diagonal elements only. Sum of the cofactors of diagonal elements only. Already we know that the method of finding the cofactor of element only. We have written the method of finding the minor of an element, cofactor of element in the second subtopic, inverse of a matrix only. Right? Now, without writing the cofactors minus, here directly we can add the 3 second order determinants only without finding the minor cofactor only. That is like this. In the given 3 by 3 matrix, consider very first 2 by 2 matrix determinant. That is here. A11, A12, A21, A22. Next, last 2 by 2 matrix determinant. Here, A22, A23, A32 or A33. Right? Next. Other one is only corner elements determinant. Only corner elements determinant. That is A11, A11, A13, A31, A33. That's all. Like this we can write. Without finding the minor cofactor, directly we can add the in the 3 by 3 matrix, very first 2 by 2 matrix determinant, very last 2 by 2 determinant, only corner elements determinant. Directly we can add the like this third order characteristic equation. So for 2 by 2, for 3 by 3, because we have the problems, gate question problems on 2 by 2, 3 by 3 only. That is why we have to remember these two only. For any order square matrix, in the characteristic equation, last term is determinant. Last term is determinant. In the second term, the quotient of the, quotient is sum of the diagonal elements in a matrix only. So the quotient of this lambda square in the third order equation is the trace of the matrix. The quotient of this lambda in the second order equation is the trace of the matrix only. So for any order square matrix in the characteristic equation, last term is a determinant and second term quotient is trace of the matrix only. Next definition, orthogonal vectors. Or perpendicular vectors only. Vectors. The two vectors. Here I am taking the two column vectors of order 3. We can add the row vectors or column any one. Capital X equal to x1, x2, x3. And capital Y equal to y1, y2, y3 are said to be an orthogonal vectors if x dot y equal to 0. That is, dot product is 0 between two vectors. Between two vectors, dot product is 0. The two vectors are called perpendicular vectors or orthogonal. Or the sum of the products of corresponding components is 0. That is, x1 into y1 plus x2 into y2 plus x3 into y3 equal to 0. Sum of the products of corresponding components. Or these two are conditions for orthogonal or perpendicular using the vector theory. In matrix theory, condition is like this: x transpose into y equal to 0. Because it is 3 by 1, it is 3 by 1 vector. The output should be here 0, that is single element or single 1 by 1 matrix only. To get 1 by 1 matrix, for the first matrix or first vector, we take the transpose. So when take the transpose of this, that becomes 1 by 3. 1 by 3, 3 by 1. Then that becomes 1 by 1, that is 0. Or if you take the first position y, then y transpose into x equal to 0. Like this. It is a condition for orthogonal vectors. Example. X equal to 1, 0, minus 2 and y equal to 0, 1, 0. Now we check whether these two are orthogonal or not. Here x dot y equal to x transpose y equal to y transpose x equal to 1 into 0 plus 0 into 1 plus minus 2 into 0. 0, 0, 0 equal to 0. Dot product is 0, or x transpose y is 0, or y transpose x is 0. Therefore, the two vectors are orthogonal or perpendicular only. Therefore, x and y are orthogonal. Right? Now here, just observe if we consider the three vectors x, y, z, among the three vectors, three pairs of vectors possible. Three pairs. That is, xy is one pair, xz is one pair, yz is one pair. Among the three vectors, we can write the three pairs. Every pair is orthogonal. Every pair is orthogonal. That is, x dot y equal to 0, x dot z equal to 0, y dot z equal to 0. Then we can say that the three vectors are pair-wise orthogonal. The three vectors are called pair-wise orthogonal. Among the three vectors, three pairs possible. Every pair is orthogonal. Then the three vectors are called pair-wise orthogonal. Pair-wise orthogonal. From this topic, all the problems will depend on the properties only. If you know the properties, we can do the problems. And also we can choose answer from the options directly by verification only, according to the properties only. All the problems of this subtopic will depend on properties. And also every property is a gate question only. So next we read the properties of eigenvalues and eigenvectors. Properties of eigenvalues and eigenvectors. The first property. In the first property, we read the 3 by 3 matrices. Matrix A equal to 3 by 3 with the general elements A, B, C, 0, D, E, 0, 0, F. Already we know that it is a upper triangular matrix, right? Which implies lambda equal to A, comma, D, comma, F. because lambda is the eigenvalue of matrix. For this upper triangular matrix, eigenvalues are just its diagonal elements, A, D, F only. Next, A equal to 3 by 3 matrix, A 0, 0, B 0, sorry, not 0, this is C, 0, D, E, F. For this lower triangular matrix, eigenvalues are its diagonal elements. A 0, 0, 0, B 0, 0, 0, C. For this diagonal matrix, eigenvalues are its diagonal elements. B 0, 0, 0, B 0, 0, 0, B. For this matrix, eigenvalues are its diagonal elements because it is a scalar matrix. B, B, B. 1, 0, 0, 0, 1, 0, 0, 0, 1. For this matrix, eigenvalues are its diagonal elements 1, 1, 1. First one is upper triangular, second one is lower triangular, third one is diagonal, next one is scalar matrix, next one is unit matrix. Next, zero matrix. 0, 0, 0, 0, 0, 0, 0, 0, 0, which implies its eigenvalues are 0, 0, 0. From all this, we can set the eigenvalues of upper triangular, lower triangular, diagonal, scalar, unit matrix, and zero matrix are its diagonal elements. For all this, if you are given matrix and if you are asked to find the eigenvalues, first you have to check that matrix is in the form of any one of these or not. The given matrix is in the form of any one of these. Directly we can tell the eigenvalues without doing the problem. Right. Next, property number 2. If lambda 1, lambda 2, and so on, lambda n are the eigenvalues of a matrix an cross n, then the first bit, because nth order matrix will have n number of eigenvalues only. For A, lambda is the general eigenvalue, then this matrix will have n eigenvalues. So particular eigenvalues are lambda 1, lambda 2, and so on, lambda n only. General eigenvalue is lambda, particular eigenvalues are like this one. For nth order matrix, n eigenvalues exist. For second order, 2 eigenvalues. Third order, 3 eigenvalues. The first result is lambda 1 plus lambda 2 plus and so on plus lambda n equal to TR of an cross n. TR of an cross n means trace of the matrix. Trace means here sum of the diagonal elements. A11 plus A22 plus and so on plus AN. Sum of the eigenvalues of square matrix equal to sum of the eigenvalues of square matrix equal to sum of its diagonal elements. Next, product of eigenvalues. Lambda 1 into lambda 2 into and so on into lambda n equal to determinant of an cross n. Product of eigenvalues is determinant of n. Next, third bit. The eigenvalues of a matrix A power m or eigenvalues of a matrix A power m or lambda 1 power m comma lambda 2 power m and so on lambda n power m, since m belongs to capital N, that is the power should be positive integer power. Suppose A has eigenvalue lambda, then A square will have an eigenvalue lambda square. Similarly, for A power 3 matrix, eigenvalue will be lambda power 3 only. So if we know the eigenvalues of matrix A, we can add the any power matrix eigenvalues like this. Next, fourth bit. The eigenvalues of a matrix Ka. That is, Ka means here scalar multiple of matrix, or the eigenvalues of scalar matrix, eigenvalues of a matrix Ka are the same as the eigenvalues of this matrix A into K. That is K into lambda 1, comma K into lambda 2, and so on, K into lambda n, since K is non-zero scalar. Next, the eigenvalues of a matrix A inverse, or one by lambda 1, comma 1 by lambda 2, and so on, comma 1 by lambda n, since determinant of A not equal to 0. The eigenvalues of a matrix adjoint of A are determinant of A by lambda 1, comma determinant of A by lambda 2, and so on, determinant of A by lambda n, comma within the brackets, since determinant of A not equal to 0. If A has eigenvalue lambda, then A inverse matrix will have an eigenvalue 1 by lambda. That is, the inverse matrix eigenvalue is the reciprocal of this only. The eigenvalues of a matrix A naught I plus A1A plus A2A square, or A naught plus A1 lambda 1 plus A2 lambda 1 square, comma A naught plus A1 into lambda 2 plus A2 into lambda 2 square, comma, and so on, comma A naught plus A1 into lambda n plus A2 into lambda n square. For this matrix of the form, these are the particular eigenvalues. If you know the eigenvalues of matrix A, we can add the eigenvalues of any matrix of the form like this. So A has eigenvalue lambda, then we can write the eigenvalues of this form: A naught plus A1A plus A2 A square. If lambda is a general eigenvalue of A, then we write the general eigenvalue of this matrix. After that, we can add the particular eigenvalues of these. If lambda is a general eigenvalue of A, then its general eigenvalue will be like this. Replace A, that is, replace every matrix with their general eigenvalue only in this. A naught into I, that is unit matrix only. For a unit matrix, eigenvalue is 1 plus A1. A has general eigenvalue lambda. In place of A, lambda A2. According to this property, third result, A square eigenvalue will be lambda square. This is the general eigenvalue only of this matrix only. For lambda, if we have a particular values, lambda 1, lambda 2, lambda 3, and so on, lambda n, we substitute here lambda 1, lambda 1, lambda 2, lambda 2, lambda 3, lambda 3, and so on, lambda n, lambda n. Like that, we can add the particular eigenvalues. This is second property. Next, property number 3. If A plus IB After this, within the brackets, or A plus root of B. That is, we are writing two properties at a time. Is an eigenvalue of a real matrix A n cross n, then A minus IB, after this within the brackets, A minus root of B is also another eigenvalue of the same matrix A n cross n. This property works only for real matrix. For any real matrix, if we know the one of the eigenvalue, then we can add the other eigenvalue of the same matrix. That is, one of the eigenvalue is the eigenvalue of real symmetric matrix is complex. That is like this 2 minus 3i. Then we can add the other eigenvalue. It's conjugated 2 plus 3i. One of the eigenvalue is surd 2 plus root 5. Then other eigenvalue will be its conjugate surd 2 minus root 5 only. For real matrix, one of the eigenvalues like this complex, then we can add the other eigenvalue. For real matrix, one of the eigenvalues surd, then we can add the other eigenvalue, conjugate surd only. That is, pair of conjugate complex exist, pair of conjugate surds exist for real symmetric matrix. Fourth one. The eigenvalues of a real symmetric matrix. The eigenvalues of a real symmetric matrix are always real. That is, real numbers only. Never be imaginary only. That is, real numbers. And the eigenvalues of a real skew symmetric matrix are either 0 or purely imaginary. This property is also for real matrices only. That if the matrix is real symmetric, its eigenvalues are always real numbers only. Suppose if it is real skew symmetric matrix, the possible eigenvalues are either 0 or purely imaginary. Example, A equal to 4, 2, 2, 4. It is a real matrix because all the elements are real, and also symmetric because A12 equal to A21 only. Then its eigenvalues are 2, 6. Both eigenvalues are real numbers, not imaginary, not complex only. So for real symmetric matrix, eigenvalues are always real numbers. Example number 2, matrix A equal to 0, 4, minus 4, 0. It is a real matrix and also skew symmetric matrix because along the diagonal, all the elements are zeros and other elements are like this. A12 equal to minus A21. It is a real skew symmetric matrix. Its possible eigenvalues are. Already we know the direct formula for, we know that the direct formula of characteristic equation of 2 by 2 matrix, lambda square minus A plus D into lambda plus determinant of A equal to 0. Using this, if you write the characteristic equation of this matrix, lambda square minus trace is 0 into lambda plus determinant is 0 minus plus 16. That is lambda square minus plus 16 equal to 0. So plus or minus 4i. So for real symmetric matrix, eigenvalues are either 0 or purely imaginary one. This matrix is, again we go back to the previous property. See this result. Here product of eigenvalues equal to determinant of A only. Out of n eigenvalues, one of the eigenvalues 0, this product is 0, determinant is 0 only. So matrix is singular means one of the eigenvalues should be 0, or one of the eigenvalues is given as 0, then the matrix is singular only. Now here it is a 2 by 2 matrix and also non-singular. Because of non-singular, all eigenvalues should be non-zero numbers. These are non-zero numbers. That is, 0 is not an eigenvalue for this real skew symmetric. If it is third order, one of the eigenvalues should be 0, other eigenvalues are purely imaginary. Now from the previous property, third property, one of the eigenvalues is complex, then its conjugate is also other eigenvalue. That is pair of conjugate complex only. Now see this example 2 in the property number 4. One of the eigenvalues is complex, then its conjugate is also other eigenvalue. So pair of conjugate complex exists. This is the example of the previous property. Next, property number 5. The eigenvectors of a real symmetric matrix are always pairwise orthogonal. That is, for 2 by 2 matrix, 2 eigenvalues are possible. For each eigenvalue, we can find the eigenvector. And between these two, if we find the dot product, this dot product will be 0. That is the condition. The matrix is real symmetric. The eigenvectors of this matrix are always pairwise orthogonal only. We can say example. A equal to 3, 4, 4 minus 3. Eigenvalues are lambda 1 equal to 5, lambda 2 equal to minus 5. If you find the eigenvector, then the corresponding eigenvectors are like this: 2, 1, x2 equal to 1 minus 2 only. The eigenvector is the non-zero solution of the homogeneous system A minus lambda I into x equal to O. Correspond to scalar lambda. This lambda is eigenvalue, this solution is the eigenvector. Just I took the one example here. For this 2 by 2, if you find eigenvalues, we get like this: 5 minus 5. And the eigenvectors, if you find the eigenvectors correspond to eigenvalues 5 minus 5, then we get the eigenvectors like this. Now we check whether these two eigenvectors are pairwise orthogonal or not. That is, between these two dot product is 0 or not, we check it only. x1 dot x2 equal to x1 dot x2. 2 into 1, 2 plus 1 into minus 2, minus 2. 2 minus 2, 0. That's it is example. For real symmetric matrix, after finding the eigenvectors, if you find the dot product between two different eigenvectors, the eigenvectors are always orthogonal only. Suppose for 3 by 3 matrix, if we have a 3 eigenvectors, then they are pairwise orthogonal. Here only 2, so 1 pair only. Next, property number 6. if the nth order matrix A has, or n cross n, has n different eigenvalues, lambda 1 comma lambda 2 and so on lambda n. The nth order matrix A n cross n has n different eigenvalues. Then the nth order matrix, A n cross n will have n linearly independent eigenvectors. X1, X2, and so on, Xn. Suppose 3 by 3 matrix has three. First of all, for 3 by 3 matrix, 3 eigenvalues exist. Lambda 1, lambda 2, lambda 3. Out of 3 eigenvalues, all 3 eigenvalues may be same, all 3 eigenvalues may be different, or some eigenvalues may be same one. Suppose all eigenvalues are different, lambda 1 not equal to lambda 2 not equal to lambda 3, all are different, then the corresponding eigenvectors are always linearly independent. Suppose 3 by 3 matrix has 3 different eigenvalues, this will have n 3 different eigenvectors. That is, if this 3 by 3 has 3 different eigenvalues, then this matrix will have 3 linearly independent eigenvectors. 3 different eigenvalues, 3 linearly independent eigenvectors. Suppose some eigenvalues are repeated, we cannot say. In such case, we use the next property only, property number 7. The next property gives the number of independent eigenvectors corresponding to any eigenvalue only. Or if you want to write the example for this property, you can write same example. A equal to 3, 4, 4 minus 3. For this matrix, lambda 1 equal to 5, lambda 2 equal to minus 5. Correspond to this eigenvector x1 equal to 2, 1, x2 equal to 1 minus 2, 1. Now this matrix has 2 different eigenvalues. Whenever the matrix has 2 different eigenvalues, this matrix will have 2 linearly independent eigenvectors. Or we can check whether these 2 independent or not. If we are given only 2 vectors, directly we can say that independent or not, just by observation only. The 2 given vectors are same, proportional, dependent, not same, not proportional, independent. So here these 2 are not same, not proportional, therefore linearly independent. Next, property number 7. The number of linearly independent eigenvectors, the number of linearly independent eigenvectors of matrix A n cross n corresponding to any eigenvalue lambda is given by P equal to n minus r, comma, where r equal to rank of characteristic matrix A minus lambda I, and n equal to number of variables in eigenvector or order of the matrix. So these are the properties. All the properties are completed. Next, we do the problems on this. Problem number 1. First problem. If A equal to 3 by 3 matrix with elements 8 minus 6, 2 minus 6, 7 minus 4, 2 minus 4, 3, then the eigenvalues of A are option A 8, 7, 3, option B 0, 3, 15, option C 1, 2, 3, option D 1, minus 1, 2, 1. We are given 3 by 3 matrix and we are asked to find its eigenvalues only. The general method to find the eigenvalues is for any square matrix. To find the eigenvalues of any given square matrix, just consider determinant of A minus lambda I and equate this to 0, solve for lambda. This is called characteristic equation, eigenequation of this matrix. For given matrix A n cross n, first write the A minus lambda I matrix, take the determinant equal to 0 and solve for lambda only. It is a general method. But here without this general method, if it is possible to choose answer, we can choose using the properties from the options. First of all, for 3 by 3 matrix, for this given 3 by 3, only 3 eigenvalues exist. Only 3 eigenvalues exist. Okay. In any one option, 3 eigenvalues are given. In any one option, 3 eigenvalues are given. That is the answer. But here, all options are containing 3 eigenvalues. So we cannot choose. Only in one of the options, 3 numbers are given. In other options, 2, 4, 5, 3 numbers will be correct answer directly. But here we cannot choose because all options are with the 3 numbers. Next, we try for the first property. This is the first property. If the given matrix is in the form of any one of these, directly we can say that eigenvalues. But our given matrix is not in the form of upper triangular, not in the form of lower triangular, diagonal, scalar, unit, like this one. So this property doesn't work only. Then we try for the next property. The next property is like this. Sum of the eigenvalues equal trace or product of eigenvalues of determinant only. Using the one of the first result or second result, we can choose the answer. Or using, if it is not possible to choose answer by using first result, then we try for the second result only. Sum of the eigenvalues is trace. What is the trace here? 8 plus 7 plus 3, 18. In any one option, sum of all the 3 numbers is 18. That is the correct answer only. Sum of these 3, 18 may be answer. Very first option is satisfied with the sum. So we cannot stop, we cannot choose this as correct answer because more than one option may satisfy this sum. So we try for other one. Sum of all these numbers also 18 may be answer. Sum of all these not 18, this is wrong. Sum of all these not 18, this is wrong. So out of these two, one of the options should be corrected. By using this sum of the eigenvalues equal to trace, we are unable to choose answer. Then we try for next result in the second property. Next result is product of eigenvalues equal to determinant. Just we find the determinant of this given matrix. Using this, we can find the this because determinant is same as product of numbers only. This value is the product of these 3 or product of these 3. Check it only. the determinant is product of this, that this will be correct, or this will be correct or not. Okay, let us write the solution. Let for this 3 by 3, 3 eigenvalues exist. Let us suppose the 3 eigenvalues are lambda 1, lambda 2, lambda 3 only. Lambda 1, lambda 2, and lambda 3 be the required eigenvalues of a 3 by 3 matrix A. Then first bit, lambda 1 plus lambda 2 plus lambda 3 equal to trace. And the second result, lambda 1 into lambda 2 into lambda 3 equal to determinant of A, which implies lambda 1 plus lambda 2 plus lambda 3 equal to trace is 18. And lambda 1 into lambda 2 into lambda 3 equal to determinant. Determinant is here 0. By using the first equation, we are unable to choose answer because the first equation is satisfied with 2 options. That is why we try for the second equation. Here, the second option will satisfy with, because product of eigenvalues is 0, means product of these 3 is 0. That's this is the answer. Product of these 3 numbers is not equal to 0. This is wrong. Here, the 2 equations (1) and 2 satisfy with the option B only. Therefore, option B is correct. That is, eigenvalues are 0, 3, 51. Hence, lambda 1 equal to 0, lambda 2 equal to 3, and lambda 3 equal to 15 only. These are the required eigenvalues. We need not to write all this, just by verification we can choose answer. Next, problem number 2. The number of distinct eigenvalues of the matrix A equal to nth order matrix with all elements as 1, 1, and so on, 1, 1, and so on, 1, 1. Is, so number of distinct eigenvalues of matrix R. Option A 0, comma n. Option B 1, comma n minus 1. Option C 0, comma n minus 1. Option D 1, comma n. We are given nth order matrix and we are asked to find the number of distinct eigenvalues. First of all, for this nth order matrix, n eigenvalues exist. Out of n eigenvalues, all eigenvalues may be different, 2 may be different, 3 may be different, 4 may be different, like this. So we require that different eigenvalues. But according to options, in every option only 2 numbers are given. So this matrix will have only 2 different eigenvalues. Have to find the 2 different eigenvalues. But finding the determinant of A minus lambda I equal to 0 is not an easy only, because it is nth ordered. Finding the determinant of nth order is not an easy. That is why we choose the particular order matrix and we generalize for this general order. Let us start with the 2 by 2 matrix. Consider A equal to 1, 1, 1, 2 by 2 matrix. For this 2 by 2 matrix, two eigenvalues exist. Now directly we can tell the eigenvalues of this matrix, because this matrix is singular. Because of singular matrix, one of the eigenvalues should be 0. And sum of the eigenvalues lambda 1 plus lambda 2 equal to trace, that is 2. Already one eigenvalue is 0, then lambda 2 equal to 2. So eigenvalues are 0 and 2 only. For this matrix, eigenvalues are 0 and 2, or lambda square minus 1 plus 1 lambda plus determinant equal to 0. Therefore, lambda equal to 0, 2 or eigenvalues. For this 2 by 2 matrix, eigenvalues are 0, 2 only. Next, we consider the third order matrix. 1, 1, 1, 1, 1, 1, 1, 1, 1. 3 by 3 matrix. It is a singular matrix. Because singular, one of the eigenvalue must be 0. But we cannot say only one eigenvalue as 0, only 2 as 0 only. But minimum one eigenvalue must be 0 because of singular matrix. Now to write the eigenvalues, directly we cannot say like previous 2 by 2 matrix. We should write the characteristic equation. Already we know the formula of characteristic equation of 3 by 3 matrix. Lambda cube minus trace 1 plus 1 plus 1 into lambda square plus sum of the 3 second order determinants. Very first 2 by 2, 0, next 0, next 0 into lambda minus determinant is also 0. Very simple equation. Lambda square into lambda minus 3 equal to 0. Therefore, lambda equal to 0, 0, 3 are the eigenvalues. Now, just by observation of these two matrices eigenvalues, we can tell the eigenvalues of this nth order matrix, so that we can add the number of different eigenvalues also. For 2 by 2 matrix, eigenvalues are 0, 2. For 3 by 3, eigenvalues are 0, 0, 3. Out of these three numbers, only two numbers are different. Here, two numbers are different. Next, for 2 by 2 matrix, eigenvalues are 0, 2. For 3 by 3, 0, 0, 3. For all these, one non-zero number, other eigenvalues are zeros only. Like that, for nth order, one eigenvalue must be n, other eigenvalues must be zeros only. For third order, one eigenvalue is 3. For second order, one eigenvalue is 2. In general, for nth order, one eigenvalue is n, other eigenvalues are zeros only. So in general, the eigenvalues of given nth order matrix A n cross n or lambda equal to n, 0, 0 and so on 0. Total number of eigenvalues is n. Out of n, one eigenvalue is n. Other must be zeros. That is how many times here? N minus 1 times. So for how many numbers are different here? Two numbers. Therefore, the different eigenvalues of a given matrix A n cross n are 0 and n. So answer is A. Next, problem number 3. Consider the matrix A equal to 3 by 3 matrix 2, 1, 1, 2, 3, 4, minus 1, minus 1, minus 2. whose eigenvalues are 1 minus 1 3 full stop, then the trace of a power 4 minus 3a cube is we are given 3 by 3 matrix along with its eigenvalues. The 3 by 3 matrix will have 3 eigenvalues, 1 minus 1 3 or the eigenvalues, and we are asked to find the trace of this matrix. Trace of this matrix a power 4 3 a cube only. Trace of this. Trace of this means sum of the diagonal elements of this matrix. Already we know that A with the elements. From this we can find the A power 3, A power 4, so that we can write the matrix A power 4 minus 3 A cube. If you know the elements of this, we can write the sum of the diagonal elements. That is a trace. Without finding the powers A power 3, A power 4 matrix, without finding these elements of the matrix, directly we can write the trace of this also using eigenvalues. Without finding the matrix elements, we write the trace of this matrix using the eigenvalues also according to second property, first result. So using second property, first result, if you want to write the trace of this matrix, we should know the eigenvalues of this matrix A power 4 minus 3 A cube. To write the eigenvalues of this matrix, we use a second property, last result. Second property, last result. Here A has general eigenvalue lambda, then A power 4 minus 3A cube will have a general eigenvalue like this. To write the general eigenvalue like lambda for A of this matrix, we replace each matrix with their general eigenvalue only. A power 4 general eigenvalue is lambda cube minus A cube general, A power 4 will have lambda power 4 minus 3, 3. In place of A cube, we write the lambda cube. So this is the general eigenvalue of this matrix of the form. But for lambda, already we know the particular values which are given 1 minus 1, 3. Now similarly for this also we write the particular eigenvalues. 1 minus 1, 3 or the eigenvalues of matrix A. Then we write the eigenvalues of this matrix only. Lambda power 4 minus 3 lambda cube. Substitute each value in this, write the corresponding value. First, lambda equal to 1. 1 power 4 minus 3 into 1 power 3 equal to 1 minus 3 minus 2. It is one of the eigenvalue of this matrix. Next, correspond to minus 1. Minus 1 power 4 minus 3 into minus 1 power 3 equal to. This is 1 minus plus 1 plus 3, 4. Next, correspond to 3. 3 power 4 minus 3 into 3 power 3. 0. 3 power 4, 3 power 4. If these three are eigenvalues of matrix A, then these three will be the eigenvalues of matrix A power 4 minus 3 A cube. When these are the eigenvalues of A, these are the eigenvalues of this matrix only. If you know the eigenvalues of this, we can have the trace. Therefore, trace of A power 4 minus 3A cube equal to sum of these minus 2 plus 4 plus 0 equal to 2. It is a trace of the matrix. Like this, for any big matrix of this form, we write the general eigenvalue like this, and then we write the particular eigenvalues like this, with the help of particular eigenvalues of A only. Next, problem number 4. Let A be a non-zero upper triangular matrix all of whose eigenvalues are 0. Full stop. Then I plus A is option A singular, option B invertible, option C symmetric, option D skew symmetric. So you have to check this matrix is symmetric or skew symmetric or singular or invertible. Invertible means inverse exists. The matrix is non-singular, inverse exists. Inverse exists, the matrix is invertible matrix. So indirectly you have to check the non-singular or not. So let us consider any order upper triangular matrix. Upper triangular matrix means in a square matrix, all the elements below the diagonal should be 0 only. Next, one more condition here. What is the condition here? Whose eigenvalues are zeros only. According to first property of eigenvalues, for upper triangular matrix, eigenvalues are its diagonal elements. Eigenvalues are its diagonal elements only. So we should take the upper triangular matrix with the diagonal elements as zeros because eigenvalues are already zeros. Let A equal to 3 by 3 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 by 3 matrix. According to definition of upper triangular, below the diagonal elements should be zeros. That is, these are the zeros only. Next, one more condition is whose eigenvalues are zeros. For upper triangular matrix, eigenvalues are diagonal elements. Eigenvalues are already zeros means diagonal elements should be zeros only. 0, 0, 0. Only these are the non-zero numbers. A, B, C on. Be the upper triangular matrix. Be the upper triangular matrix with eigenvalues 0. Or all of whose eigenvalues are 0. Then I plus A. I is the unit matrix. Here we have taken the 3 by 3 only. So we take the I3 only. I plus A equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Plus A, 0, A, B, 0, 0, C, 0, 0, 0, which implies I plus A equal to 3 by 3 matrix. When you add these two matrices, 1, A, B, 0, 1, C, 0, 0, 1. It is a resulting matrix I plus A. Now check whether it is symmetric, skew symmetric, or singular, non-singular, like this. First of all, it is not a symmetric matrix, not a skew symmetric. So these two are wrong. So either it should be singular, non-singular. But it is an upper triangular matrix. Determinant of upper triangular matrix is product of diagonal elements, which implies determinant of I plus A equal to product of diagonal elements equal to 1, not equal to 0. Therefore, which implies I plus A is invertible non-singular matrix. Non-singular matrix. Therefore, I plus A is invertible. Because its inverse exists. So singular is wrong, then B is correct. Next, problem number 5. If the characteristic equation characteristic polynomial, not equation. Characteristic polynomial of a 3 by 3 matrix capital M over R. After this, within the brackets, the set of all real numbers is lambda cube minus 12 lambda square plus A into lambda minus 32 2 comma A belongs to R. A belongs to R, and one of the eigen value of M is 2, then the largest eigenvalue, the largest among the absolute values of the eigenvalues of M is. It is a 2017 2 marks problem, fill in the blank question. For some 3 by 3 matrix capital M, we are given characteristic polynomial. And if we equate these to 0, we get characteristic equation. And also one of the eigenvalues is also given. For 3 by 3 matrix, 3 eigenvalues exist. Out of 3 eigenvalues, already one of the eigenvalues is given. This is one of the eigenvalues. It is a characteristic polynomial. And one of the unknown quotient A. So we are asked to choose a largest eigenvalue among all the absolute values of eigenvalues. Suppose all eigenvalues are positive, then we choose the largest one only. Suppose some eigenvalues are negative, also we take the absolute values. Among that absolute values, we choose the largest one. So first we have to find the two eigenvalues of this matrix. Already one of the eigenvalues known, then we try to find the other two eigenvalues of same matrix only. Let lambda 1, lambda 2 and lambda 3 equal to 2. Let us suppose one of the eigenvalues is 2 and required eigenvalue is lambda 1, lambda 2. Be the eigenvalues. Be the eigenvalues of a matrix M. Then, according to second property first result, sum of the eigenvalues lambda 1 plus lambda 2 plus lambda 3 equal to trace of the matrices. From this given characteristic polynomial, we can tell the trace. The trace is same as the sum of the eigenvalues, that is same as the quotient of lambda square. So 12, this is given. And product of eigenvalues lambda 1 into lambda 2 into lambda 3 equal to 32. That is same as constant term, this constant term only. Okay. So from this characteristic polynomial, the quotient of lambda square is the trace and the last term without lambda is the determinant only. That is product of eigenvalues. But lambda 3 is already 2. From these two, we write the equations as lambda 1 plus lambda 2 equal to 12 minus 2, that is 10. And lambda 1 into lambda 2 equal to 32 by 2, that is 16. So we know the sum of the two numbers, product of two numbers. Now we can solve these two equations for lambda 1, lambda 2. Then we get the all three eigenvalues. We can use any method to find the one of the eigenvalue. Now I'm using the a plus b whole square minus a minus b whole square equal to 4ab formula. Lambda 1 plus lambda 2 whole square minus lambda 1 minus lambda 2 whole square equal to 4 into lambda 1 into lambda 2, which implies lambda 1 minus lambda 2 square equal to lambda 1 plus lambda 2 whole square, that is 10 square minus 4 into 16, which implies lambda 1 minus lambda 2 equal to plus or minus 100 minus 64, 36 root then 6 on. So we can solve lambda 1 plus lambda 2 equal to 10 and lambda 1 minus lambda 2 equal to 6. Here we can take any one, lambda 1 minus lambda 2 equal to plus 6 or lambda 1 minus lambda 2 equal to minus 6. Any one we can choose. Solving lambda 1 plus lambda 2 equal to 10 and lambda 1 minus lambda 2 equal to plus 6 or minus 6, any one, we get lambda 1 equal to 8 and lambda 2 equal to 2 only. Right? But here all the eigenvalues are positive. Because of positive, out of 2 to 8, the largest one is 8. Therefore, the largest eigenvalue of a given matrix M3 by 3 is 8. Or other method is solving this equation. Just equate this polynomial to 0 and solve it for lambda. But one of the unknown quotient is given a. To get this a, we substitute lambda equal to 2 because already one of the eigenvalues is 2 only. Substitute lambda equal to 2, we get a value. After that, substitute a here and equate to 0, solve for cubic equation. Also, we can get the lambda 1, lambda 2, lambda 3. Anyway, we can do one. Next, problem number 6. An eigenvector corresponding to the smallest eigenvalue of the matrix with elements 1 1 minus 1 2 0 2 0 1 0 0 minus 1 1 0 0 0 0 is option A 1 0 0 0 power t, option B 1 1 0 0 power t, option C 1 0 2 0 power t, option D the eigenvector is minus 1 2 2 power t. So we are given 4 by 4 matrix and we are asked to find the one of the eigenvector corresponding to this smallest eigenvalue of the matrix. Even though it is 4 by 4 matrix, directly we can tell the eigenvalues of this matrix. If you know the eigenvalues, we can choose the smallest number. Corresponding to the smallest number, we try to find the eigenvector, right? Because it is upper triangular matrix. It is a upper triangular matrix. Because upper triangular matrix, its eigenvalues are diagonal elements. These are the eigenvalues. Out of all this, the smallest number is minus 1. So corresponding to minus 1, we need to find the eigenvector only. The general method is like this. For any square matrix, first we need to find the eigenvalues. To find the eigenvalues, we consider characteristic equation, determinant of a minus lambda I equal to 0, and we solve for lambda. After getting the lambda values, for each value of lambda, we consider homogeneous system a minus lambda I into x equal to O. We solve for non-zero solution. It is a method. It is a general method. For any square matrix, if we want to find eigenvalues, eigenvectors, we do like this. Consider characteristic equation, solve for lambda. After getting the lambda values, consider homogeneous system, solve it for non-zero solution. So finding the eigenvector is same as non-zero solution of the homogeneous system only. Already we know that method of finding the solution of the system only. Here the smallest eigenvalue of a matrix A 4 by 4 is minus 1. So corresponding to minus 1, we have to find the eigenvector. Already we know the eigenvalue this lambda. So directly consider this homogeneous system, solve it for non-zero solution. Right? Now let us consider the homogeneous system A minus lambda I into x equal to O. Because of the options in the, because of the vectors in the options, for this problem options are given. So one of the options is the eigenvector of this matrix only. Because of these options, we can choose answer by verification also. But we do this problem by actual method only. In the next problem onwards, we try to choose answer by verification only. So let us do this problem by actual method only. Natural method means finding the eigenvector is solution of this system. That's which implies now write the characteristic matrix A minus lambda I only. For any given square matrix, to write the characteristic matrix, directly we can add the characteristic matrix just by adding minus lambda for diagonal elements. Just add minus lambda for diagonal. That will give characteristic matrix. So 1 minus lambda 0 0 0 along the second column 1 2 minus lambda 0 0 minus 1 0 minus 1 minus lambda 0 2 1 1 0 minus lambda into, if A is nth order, then its eigenvector should be of order n cross 1. If it is A 4 by 4 matrix, its eigenvector is 4 by 1 only. Then that will contain 4 elements x1, x2, x3, x4 equal to 0 vector 0 0 0 0. Now we have to solve this system, but in this system we have unknown scalar lambda, but unknown scalar lambda is already known here. So one of the for a given matrix smallest eigenvalue is lambda equal to -1 only, and correspond to -1 we are finding eigenvectors. So substitute lambda equal to -1 in this, which implies when you substitute lambda equal to -1, this becomes 2 1 -1 2 0 2 minus minus plus 3 0 1 0 0 -1 minus minus plus 0 1 0 0 0 plus 1 into x equal to 0 matrix. Now this is a particular homogeneous system. We solve it for solution x1 x2 x3 on x4 x1 x2 x3 x4 0 0 0 0 on, right? Already we know the method of finding the solution of the system. We have written the method of finding the solution procedure in the previous topic, solution of system of linear equations. According to that, we express the given system of linear equations in matrix form like this, Ax equal to B form. After that, we consider augmented matrix. We reduce the matrix into echelon form. But for homogeneous system, augmented matrix is same as A, because this B vector is 0 column only. With this 0 column, rank of A, rank of augmented matrix are same only. That is why we never choose augmented. Instead of choosing the augmented, we consider matrix A only. So for homogeneous system, consider matrix A and reduce the matrix into echelon form. Here it is not in echelon form. We try to reduce the matrix into echelon form because 1 less than 3, not less than 3 only. To get the echelon form, it should be 0 only. 2, 1, -1, 2, 0, 3, 0, 1, 0, 0, 0, 0. So 1. Or 4 minus R3, 0, 0, 0, 0. Now this is in echelon form. x1, x2, x3, x4 equal to 0, 0, 0, 0. After reducing the matrix into echelon form, we rewrite system of equations on, because according to fourth step, the solution exists, then the solution may be unique or infinitely many solutions. So here, solution exists. The solution exists because the homogeneous system solution always exists on it. Solution exists here on. That is why we try to write the system of equation from this Ax equal to 1. From this echelon form of the quotient matrix, rewrite system of equations and find the solution by backward substitution only. Every row is a one equation only. 2 into x1 plus 1 into x2 minus x3 plus x2 x4 equal to 0, which implies 2x1 plus x2 minus x3 plus 2x4 equal to 0. From the second equation, 3x2 plus x4 equal to 0. From the third equation, directly x4 equal to 0 only. By backward substitution, we got lost variable value. We substitute in the second equation so that we get x2 only. If we substitute x2, x4 in this first equation, we get one more equation. x4 equal to 0. If we substitute this in second equation, we get the x2 equal to 0. If we substitute these two in first equation, the equation will be 2x1 minus x3 equal to 0. x2, x4 are known, but x1, x3 are unknown only. Now we have to find x1, x3. This is the third equation is equation in two variables. Third equation is in two variables. If we give some value to x3, we get some value for x1. Let us consider x1 equal to k. Then x3 equal to 2k. Therefore, the eigenvector x equal to x1, x2, x3, x4 equal to x1 is k, arbitrary, any value, x2 is 0, x3 is arbitrary, any value, x4 is 0. Or we can add the k into 1, 0, 2, 0. It is a solution of this system only. The solution of this system is the eigenvector of matrix A. Solution of the system is the eigenvector of matrix A only. Now check whether it is given in the option or not. This is same as the option C. Therefore, C is the correct answer. It is the actual method to write the eigenvector of any given matrix. Finding the eigenvector is same as finding the non-zero solution of the homogeneous system only. But from next problem onwards, we try to choose answer by verification instead of doing the problem in this way only. Next, problem number 7. Let A equal to 3 by 3 matrix with the elements -2, 2, -3, 2, 1, -6, -1, -2, 0. Full stop. If -3 and -3 are the two eigenvalues of A, then the eigenvector corresponding to the third eigenvalue is option A 1, 2, 1 power t. Option B 1, 2, -1 power t. Option C 1, -2, 1 power t. Option D -1, 2, 1 power t. It is also similar to previous problem, but it is 3 by 3. Previous one is 4 by 4. In the previous problem, it was asked to write the eigenvector corresponding to smallest eigenvalue. Here, we are asked to find the eigenvector corresponding to third eigenvalue of this matrix only. For 3 by 3 matrix, 3 eigenvalues exist. In general, 3 eigenvalues exist. Out of 3, 2 are already given. So if you know the 2 eigenvalues out of 3, we can add the third eigenvalue using the second property, first result or second result. That is trace equal to sum of the eigenvalues. Let lambda 1 equal to -3 and lambda 2 equal to -3 and lambda 3 be the eigenvalues. of eigenvalues of a matrix A3 by 3. Then lambda 1 plus lambda 2 plus lambda 3 equal to trace, which implies minus 3 plus the third required eigenvalue. Trace is minus 2 plus 1 plus 0. Therefore, the third eigenvalue is here minus 1, minus 6 plus 6 plus 5. This is the required eigenvalue. So corresponding to eigenvalue 5, we need to find the eigenvector. If we want to do the problem by method, we can do this problem just like previous problem. For that method, we require this eigenvalue. But here, if we want to use the verification method, for verification method, we do not require this eigenvalue also. Without finding this eigenvalue, we can choose answer by verification. Now say this. By definition of eigenvector, the matrix equation is Ax equal to lambda x. Or it is also same as the A minus lambda I into x equal to O. This matrix equation satisfies or not with any one of the option, we check it on. For this, we find the product Ax for given matrix from the option vector. After that, we check whether this is equal to some scalar into the same x or not. And scalar is here 5. So this matrix equation satisfies with any option, that is the correct answer. Let us start with the first option. Consider Ax. A is minus 2, 2, minus 3. 2, 1, minus 6. Minus 1, minus 2, 0. Into x. Here x is from the first option 1, 2, 1. 3 by 3, 3 by 1, output is 3 by 1. Row, column, minus 2 plus 4 plus 2 plus 2 minus 3 minus 1. Minus 2 plus 4 plus 2 plus 2 minus 3 minus 1. 2 plus 2, 4 minus 6 minus 2 minus 1 minus 4 minus 5. Is it equal to some scalar into the same vector or not? Check it only. Can you write this vector in terms of this or not? We can write this vector in terms of this when two vectors are same proportional, but these two are not same, not proportional. So this is not equal to any scalar into the same. Ax is not equal to lambda x. Equation is not satisfied with option A. So A is wrong. Next option B. Ax. Same matrix, different vector. That is from the option B, 1, 2, minus 1 equal to. Minus 2, 1, minus 2. Minus 2 plus 4. Minus 2 plus 4. First of all, from the previous option, this option, difference is only last element. So last element will change. First two are same. Okay. Next. Minus 1, minus 4, minus 5. So this is minus 1, minus 4, minus 5. So this is different. Minus 2 plus 4 minus plus 2 plus 2 plus 3 plus 5. This is 5. 2 plus 2, 4, 4 plus 6, 10. Next, minus 1, minus 4, minus 5. Now check, are these two same or proportional? If these two are same proportional, we can express this in terms of this, so that equation will satisfy on it. But here 5 is common, 5 into 1, 1, 5, 2, 5 minus 5 into 1, 2 minus 1. This is same as lambda x. Here the equation is satisfied with the option B. Therefore, B is the correct answer. Like this, we can check the equation Ax equal to lambda x satisfies or not. This is satisfied with the second option. Therefore, second option is correct answer. Next, problem number 8. If 2 minus 2, 1 power t is an eigenvector of the matrix A, equal to 3 by 3 matrix with elements 8 minus 6, 2 minus 6, x minus 4, 2 minus 4, 3, then x equal to. We are given a matrix along with its one of the eigenvector. Already he is saying that this is the eigenvector of this matrix only. It is eigenvector of this matrix. Whenever it is eigenvector of this matrix, this equation will satisfy x equal to lambda x. So use this equation, try to find out this unknown x. That's all. Consider Ax equal to lambda x. Already this is the eigenvector of this matrix only. So this equation will satisfy. Using these equations, find out the x unknown. The matrix is 8 minus 6, 2 minus 6, minus, x minus 4, 2 minus 4, 3 on. Into x is 2 minus 2, 1 equal to lambda is unknown, 2 minus 2, 1. Actually, we require the one unknown x only, but from this equation, we are getting one more unknown. So finally, we have two unknowns. To get two unknowns, we require minimum two equations only. Every row is a one equation only. First equation is 8 into 2 plus minus 6 into minus 2 plus 2 into 1 equal to lambda into 2. From this directly we get the lambda value. Now from second equation, minus 6 into 2 plus x into minus 2 plus minus 4 into 1 equal to lambda into minus 2 on. Now solving these, we get the x and lambda value on. Now what is the lambda value? What is the x value? Tell me the values of x and lambda on. We'll take break at 7 o'clock and then we continue the topic. We'll have a break at 7 o'clock. X is 7, lambda is okay. Lambda is 15, X is 7. Just check it down. This is problem number 8. Next, problem number 9. The number of linearly independent eigenvectors of a matrix A equal to 3 by 3 matrix 1, 0, 7, 0, 2, minus 4, 0, 0, 9. The number of linearly independent eigenvectors of a matrix A is, number of linearly independent eigenvectors is, it is a 3 by 3 matrix. For 3 by 3 matrix, 3 eigenvalues exist. For each eigenvalue, we find the eigenvector because, see this. For A n cross n, to write the eigenvalues, we consider determinant of A minus lambda I equal to 0. We solve for lambda. And then, after getting the lambda value, we solve the homogeneous system for solution for each value of lambda. For this matrix, lambda 1, lambda 2, lambda 3. For lambda 1, we get x1. For lambda 2, we get x2. For lambda 3, we get x3. After getting x1, x2, x3, we check all the eigenvectors as independent or some are independent like this one. We require the number of independent eigenvectors. This is the method only. But we never do the problem in this way only. If you do like this, it takes more time. If it is possible to find the eigenvalues, find the eigenvalues first. After finding the eigenvalues, check all the eigenvalues are same, some eigenvalues are same, or all eigenvalues are different. Suppose all eigenvalues are different, according to last but one property, directly we can say that independent, number of independent only. The last but one property is, if the nth order matrix has n different eigenvalues, nth order matrix has n different eigenvalues, then the matrix will have n linearly independent eigenvectors only. Now for this given matrix, we can say that eigenvalues directly because it is upper triangular matrix. Its eigenvalues are 1, 2, 9. 1, 2, 9. Here all eigenvalues are different, not same. So whenever eigenvalues are different, directly we can write the answer. If a 3 by 3 matrix has 3 different eigenvalues, then the 3 by 3 matrix will have 3 linearly independent eigenvectors only. That's it. It is the answer. 3 is the answer. Given A equal to 1, 0, 7, 0, 2, minus 4, 0, 0, 9. Which implies eigenvalues are lambda equal to 1, 2, 9. So corresponding to each eigenvalue, we can find one eigenvector only, x1, x2, x3. So here all eigenvectors will be linearly independent. How many are independent? 3. Therefore, the given matrix A 3 by 3 will have three linearly independent eigenvectors according to property number 6. Suppose some eigenvalues are repeated, we cannot say. In such case, we use the last property number 7. Next, problem number 10. 10th problem. The number of linearly independent eigenvectors of a matrix A equal to 3 by 3 matrix 3 0 1 0 2 1 0 0 2 is similar to previous problem. We require the number of linearly independent eigenvectors of the matrix. Here it is a upper triangular matrix. Because upper triangular, directly we can write the eigenvalues. Eigenvalues are diagonal elements 3 2 2. Eigenvalues are 3 2 2. But all eigenvalues are not different. One eigenvalue is different from these two. So out of 3 eigenvalues, one of the eigenvalue is repeated 2 times. Whenever eigenvalue is repeated, directly we cannot say the number of independent. In this case, we require the formula. That formula is given by last property. According to last property, the formula is P equal to n minus r. N is the order of the matrix or number of elements in the eigenvector. For third order matrix, eigenvector is of order 3 only, 3 by 1. It will contain 3 elements, x1, x2, x3 only. So n is 3 and r. R is the rank of characteristic matrix only. So we need to find the r value correspond to this lambda equal 2 only. Given A equal to 3 0 1 0 2 1 0 0 2, which implies eigenvalues are lambda equal to 3 comma 2 comma 2. 3 is different from this. Correspond to this different eigenvalue, we get one different eigenvector. Correspond to this eigenvalue, we get one eigenvector. Corresponding to 2 times repeated eigenvalues, we may get one independent or you may get 2 independent. But either 1 or 2 corresponding to 2 is given by the formula P equal to n minus r. N is 3, r is rank of its characteristic matrix. So we need to find this P value. To get P value, we require the rank of characteristic matrix corresponding to lambda equal 2 only. So consider A minus lambda I equal to 3 minus lambda 0 1 0 2 minus lambda 1 0 0 2 minus lambda, which implies A minus lambda I equal to, when you substitute lambda equal to 2, this matrix becomes 1 0 1 0 0 1 0 0 0 for lambda equal to 1. Now find the rank if it is an echelon form. 2 zeros less than 3 zeros. So it is in echelon form, which implies R equal to rho of A minus lambda I equal to 2 only, which implies P value equal to n minus R equal to 3 minus 2 equal to 1. So corresponding to 2 repeated eigenvalues, one independent eigenvector is possible only. Correspond to 2, 1 independent, correspond to 3, 1 independent, totally 1 plus 1, 2. This matrix will have 2 independent eigenvectors only. Corresponding to repeated eigenvalue, only one independent. But corresponding to other non-repeated value, one more independent. Totally 2 independent eigenvectors. Therefore, the number of linearly independent eigenvectors of a given matrix A3 by 3 is 1 plus 1 equal to 2. It is the answer. This one is corresponding to lambda equal to 3. This another one is corresponding to lambda equal to 2 only. Totally, how many eigenvectors? 2 eigenvectors. Matrix will have 2 independent eigenvectors, but correspond to only one independent only. This one, totally 2 independent. So all eigenvalues are different. Like previous problem, directly we can tell the answer. Some are repeated. Like this, we do the problem. So next problem number 11. After 11th problem, we'll take break. If A is a skew symmetric matrix of order n, then the number of linearly independent eigenvectors of A plus A transpose is option A 0, B 1, C n minus 1, D n. 11th problem is similar to previous 2 problems, 9th and 10th. But the difference is in the first 2 problems, matrix was given along with elements. But here matrix is not given. Instead of giving the matrix along with elements, name of the matrix is given. What is the name? Skew symmetric. And we are asked to find the number of independent eigenvectors corresponding to this matrix. We do not require the number of independent eigenvectors of this matrix. We require the number of independent eigenvectors of this matrix. A is a skew symmetric. Condition for skew symmetric is A transpose equal to minus A. So given that A transpose equal to minus A. Now to find the number of independent eigenvectors of this matrix, let us suppose this matrix as some new matrix B only. For our convenience, we write the A plus A transpose as single matrix B only. Let B equal to A plus A transpose. Then B equal to A, but from the given data A transpose is minus A. So here minus A, which implies 0 matrix. Finding the number of independent eigenvectors of A plus A transpose is same as finding the number of independent eigenvectors of 0 matrix only, indirectly. That is, this is a 0 matrix only. For 0 matrix, we know that eigenvalues, which implies the eigenvalues of B matrix or lambda equal to 0, 0, and so on 0. Anytime, how many times? N times, because of nth order. So up to here we know that eigenvalues, but all eigenvalues are not repeated, not different. Here all eigenvalues are not different, all are repeated. Because they're repeated, directly we cannot say the number of independent. In this case, we require the formula P equal to n minus r. Right? Now, the number of linearly independent eigenvectors of a matrix B equal to A plus A transpose equal to 0 matrix is given by P equal to N minus R, N equal to N, because order of the matrix is N. Eigenvector will contain n elements. R is row of B minus lambda I, which implies P equal to N minus row of, but B is 0 matrix. For 0 matrix, eigenvalue is 0. So 0 into I, which implies P equal to N minus row of 0 matrix minus 0 into I matrix is 0 matrix. Finally, it is rank of 0 matrix equal to N. Therefore, P equal to N minus 0 equal to N. It is the answer. Number of independent eigenvectors is N. So this 0 matrix will have N linearly independent eigenvectors corresponding to N times repeated eigenvalue 0. So with this, problems on eigenvalues and eigenvectors are completed. Problems on eigenvalues and eigenvectors are completed. Now we'll take break. After the break, we start the Cayley-Hamilton theorem, and then we do the, that is, we discuss about LU decomposition. With that, topic will be completed. So after 20 minutes, we start. After 20 minutes, we start. Okay, let us start the class. Break is completed. So before the break, we have completed the problems on eigenvalues and eigenvectors. Now we start the Cayley-Hamilton theorem. Cayley-Hamilton theorem. In short form, C.H.T. The statement of this theorem. Every square matrix satisfies its own characteristic equation. Every square matrix satisfies its own characteristic equation. This is the statement of the theorem. Every square matrix satisfies its own characteristic equation, not other sum. Example, if lambda square minus 8 lambda plus 12 equal to 0 is a characteristic equation of a matrix A equal to 4, 2, 2, 4, then by Cayley-Hamilton theorem, we have, according to theorem, the matrix A has to satisfy this equation. Matrix A has to satisfy its characteristic equation. Satisfying means in place of lambda, write the matrix A on it. So first term is lambda square, that is A square minus 8, 8 in place of lambda A plus 12, 12. We are writing matrix equation. Simply we cannot write constant. So constant into unit matrix equal to, again 0 into I, that becomes 0 matrix. Now this is a relation. This Cayley-Hamilton theorem gives the relation between square matrix and its characteristic equation. The theorem is giving this relation between the matrix and characteristic equation only. Finally, we are getting matrix equation. From this matrix equation, we try to find the powers of the matrix. Only. According to theorem, we can find the powers. The matrix is non-singular. We can find the positive powers, a power 2, a power 3, a power 4, and so on. Suppose if it is non-singular, we can write the positive powers and also inverse. If the inverse exists, we can write the a power minus 2, a power minus 3, and so on. Suppose if it is only singular, only we can find the positive powers, a power 2, a power 3, and so on. Using Cayley-Hamilton theorem, we can find the powers of the matrix. Non-singular, we can find both positive and negative powers. If it is singular, only positive powers. So we can say that the Cayley-Hamilton theorem gives another method to find the positive integer powers of the matrix. And this method also gives another method to find the inverse of a matrix. If the inverse exists, we can add the other negative integer powers. Right, next problems on this. The first problem. if 1, 2, and 3 are the eigenvalues of the matrix A 3 by 3, then 6 into A inverse equal to option A square plus 6A minus 11I. Option B, A square minus 6A minus 11I. Option C, A square minus 6A plus 11I. Option D, A square plus 6A plus 11I. For some 3 by 3 matrix, already eigenvalues are given 1, 2, 3. If you know the eigenvalues of the matrix, we can write the 6A inverse. That is, we are asked to write the A inverse, but elements of the matrix are not given. If you know the elements of A, we can write the A inverse by using the adjoint method only. Here elements are not given. Instead of giving the elements of the matrix, we are given its eigenvalues. With the help of eigenvalues, we can write the characteristic equation. From the characteristic equation, we can write the matrix equation according to theorem. After writing the matrix equation, we can express A inverse in terms of all other matrices like this. Given that lambda 1 equal to 1, lambda 2 equal to 2, and lambda 3 equal to 3 are the eigenvalues of A 3 by 3 matrix, which implies the characteristic equation of A 3 by 3 matrix with eigenvalues lambda 1 equal to 1, lambda 2 equal to 2, and lambda 3 equal to 3 is given by lambda minus 1 into lambda minus 2 into lambda minus 3 equal to 0, which implies lambda square minus, first we multiply these two and then multiply this, lambda square minus 2 lambda minus lambda plus 2 into lambda minus 3 equal to 0, right? Which implies lambda cube minus 2 lambda square minus lambda square plus 2 lambda minus 3 lambda square minus 2 lambda 3 lambda square minus plus 6 lambda plus 3 lambda plus minus 6 equal to 0. Lambda cube minus 2 lambda square minus 6 lambda square, 2 lambda 8 plus 3 11 lambda minus 6 equal to 0. This is the characteristic equation only. When alpha beta roots of the equation, then the quadratic equation is x minus alpha into x minus beta. Like that, 1, 2, 3 are roots of the characteristic equation of 3 by 3 matrix. Then Lambda minus 1, lambda minus 2, lambda minus 3 is the characteristic equation only. According to theorem, the matrix equation is a cube minus 6a square plus 11a minus 6i equal to O. Now to find the A inverse, multiply both sides with a power minus 1, which implies A inverse into a cube minus 6a square plus 11a minus 6i a square minus 6a plus 11a inverse minus 6. This is 11i minus 6a inverse equal to O. Therefore, 6a inverse equal to a square minus 6a plus 11i. It is the inverse according to Cayley-Hamilton theorem. Writing the A inverse in terms of all other matrices. A square minus 6a plus 11i. This is the option. Next, problem number 2. Let A equal to 3 by 3 matrix. 1, 0, minus 1, minus 1, 2, 0, 0, 0, minus 2, and B equal to a cube minus a square minus 4a plus 6i, comma, where I is the 3 by 3 identity matrix. Full stop. The determinant of B is it is a 2 marks gate question. A is a 3 by 3 matrix along with elements, and we are asked to find the determinant of B. If you know the A, we can find the determinant of A only, but we require the B. If you know the elements of B also, we can add the determinant of B only, but elements of this matrix are not given. Instead of giving the elements of this matrix, B is given in terms of A only. B is given in terms of A. One method is substitute I, substitute A, substitute A square, substitute A cube, so that we get the elements of B. After that, we can add the determinant. That is one method. Without finding all these powers and without finding the elements of this matrix, also we can add the determinant of B only using the eigenvalues only. If you know the eigenvalues of this big matrix, we can add the determinant of this matrix, because determinant of B is same as product of eigenvalues. So let us find the eigenvalues of this big matrix, like third problem in the eigenvalues only. If you know the eigenvalues of A, we can get the eigenvalues of B also. But it is not a given matrix, is not upper triangular, not a lower triangular only. So to get the eigenvalues of this, first we should add the characteristic equation. The characteristic equation of a given 3 by 3 matrix A is lambda cube minus, already we know the direct formula for writing the characteristic equation of 3 by 3 matrix, 2 by 2 matrix only. So lambda cube minus sum of the diagonal elements 1 plus 2 minus 2 into lambda square plus very first 2 by 2 matrix 2 minus 0 2 plus very last 2 by 2 matrix minus 4 plus only corner elements minus 2 minus 0 minus 2 into lambda minus determinant of the matrix. Along the last row we have more number of zeros, so we can expand along the last row. So minus 2 into delete the corresponding row, corresponding column. 2 minus 0 minus 2 into 2 minus 4 equal to 0, which implies lambda cube minus lambda square minus 2 plus 2 minus 4 lambda plus 4 equal to 0. This is the characteristic equation. If you solve for lambda, we get the lambda values. If you know the lambda values, we can get the eigenvalues of B also. That is one method. But before going to solve this equation for lambda values, observe all the terms in the characteristic equation, all the terms in the matrix, B matrix only. A cube, lambda cube, same. A square, lambda square, same. 4A, 4 lambda, same. Only this term is different only. So because of these are the same as these terms, you need not to find the eigenvalues only. We write the matrix equation and then we write directly the determinant of B matrix only, which implies by Cayley-Hamilton theorem, we write this as A cube minus A square minus 4A plus 4I equal to O. According to Cayley-Hamilton theorem, we have this matrix equation. Let us suppose this is 1. Now we consider our given matrix, our required matrix. B equal to, B is given in terms of matrix A, that is A power 3 minus A square minus 4A plus 6I. 1, 2, 3. The first 3 terms are same as these 3 terms in the equation 1 only. So we write this 6I as 4I plus 2I. If you write this as 4 plus I and 2I up to 4, this equation is 0 matrix. B equal to A cube minus A square minus 4A. I'm writing this 6I as 4I plus 2I. And then separate this matrix. But this is same as equation 1 only. Because of this equation 1, we replace this matrix with a 0 matrix only, because sum of all this is 0 matrix only, which implies B equal to 0 matrix plus 2I, which implies B equal to 2I. Finally, the matrix is 2I. So finding the determinant of B same as finding the determinant of 2I. Therefore, determinant of B equal to determinant of 2 into I. Use the one of the property of determinants. It is in the form of determinant of scalar multiple of matrix only. Determinant of scalar multiple of matrix. This is equal to 2 power. B is a 3 by 3 matrix. A is a 3 by 3. B is also 3 by 3. This is 2 power 3 into determinant of I. This is equal to 8. Since determinant of scalar multiple of A n cross n equal to k power n into determinant of A n cross n. That's it. This is the value. Because of these terms are the same as this matrix. That is why we are doing like this without finding the eigenvalues. It is a 2 marks gate question on. So with this problem, problems on Cayley-Hamilton theorem are also completed on. With this eigenvalues and eigenvectors, Cayley-Hamilton theorem topic is completed. Next, last one, LU decomposition only. LU decomposable matrix or LU factorizable matrix if a square matrix AN cross N is written as A equal to L into U, comma, where capital L is a lower triangular matrix and capital U is a upper triangular matrix. Then the square matrix AN cross N is called LU decomposable matrix. LU decomposable matrix. That is, if you are able to write the matrix A as a product of two matrices, one of the matrices is lower triangular, other matrix is upper triangular, then we can set decomposable matrix on it. We are writing the A as a product of two. That is, we are decomposing into two matrices on it. Then the matrix is called decomposable matrix. Now to find the L and U, there are two methods. One method is called Doolittle's method, other one is Crowd's method only. Methods of finding the matrices L and U on. Now there are two methods to find the L and U matrices, in which method one is called Doolittle's method, or Doolittle's LU decomposition method. LU decomposition method. So name of the first method is Doolittle's method or Doolittle's LU decomposition method only, in which if A equal to L into U, then consider A11, A12, A21, A22 equal to lower triangular matrix into upper triangular matrix. 1, 2, 3, 4. 1, 2, 3, 4. According to lower triangular matrix, all the elements about by diagonal should be zeros only. In the lower triangular matrix, according to definition of lower triangular, all the elements above the diagonal should be zeros. According to upper triangular matrix, all the elements below the diagonal element should be zeros. Right? Next, according to this method, we write the diagonal elements as 1. Here this is L21. This is U11, U12, U122 only. This is for 2 by 2 matrix. If A equal to LU, then you then consider this 2 by 2 matrix equal to L into U for 2 by 2 matrix only. Now to find the L and U, we have to find the L21, U11, U12, U22. To find these elements, just right hand side, find the product of these two, equate the corresponding elements of this matrix and solve for L1, that is L21, U11, U12 and so on. And for similarly for 3 by 3 matrix also. A11, A12, A13, A21, A22, A23, A31, A32, A33. To write this matrix as L into U, we write the general L into U and then we try to find the elements of these two matrices. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. According to lower triangular matrix, all the elements above diagonal should be 0. According to definition of upper triangular matrix, below the diagonal, all should be zeros. Next, according to this Doolittle's methods, in the lower triangular matrix, along the diagonal, element should be 1. So other elements are L21. This is L22. So this is L31, L32. Next, in the upper triangular matrix, we take this element as U11, this as U12, this as U13. U22, U23, U33 for 3 by 3 matrix. Here, this matrix is called unit lower triangular matrix. This is called unit lower triangular matrix. In a lower triangular matrix, along the diagonal, all the elements are 1. Then the lower triangular matrix is called unit lower triangular matrix. In the upper triangular matrix, along the diagonal, all the elements are 1. Then such a matrix is called unit upper triangular matrix. So to find the L and U matrices, we do like this one according to Doolittle's method. Other method is Kraut's method only. In the Kraut's method, we consider upper triangular matrix as unit upper triangular matrix. It is only difference. Method 2. The name of the method is Kraut's method or Kraut's LU decomposition method. this method. If A equal to L into U, then consider first 2 by 2 matrix A11, A12, A21, A22 equal to L into U. L11 0, L21, L22 1, U12 0, U2. This is now this is the unit upper triangular matrix. It is the only difference. According to Doolittle's method, we consider the lower triangular matrix as unit lower triangular matrix. According to Kraut's method, we consider upper triangular matrix as unit upper triangular matrix. It is only one method. And for 3 by 3 matrix, it is for 2 by 2 matrix. A11, A12, A2, A13, 21, 22, 23, 31, 32, 33 equal to L11 0 0, L21 L22 0, L31 L32 L33 into 1 U12 U13 0 U, that is 1 U23 0 0 1. That's it. This is for 3 by 3 matrix. These are the two methods to find the L and U matrices. Later I will tell the shortcut method to find the, this method will be simple for 2 by 2 only. For 3 by 3 means it takes time only, because you have to find the product of these two. We get some matrix and we equate the corresponding elements on both sides and we solve for all the elements only. Without this also we can find the L and U matrices by using the echelon form method, row echelon form method and upper echelon form method. This finding the lower triangular matrix is same as column echelon form method, and this is finding the upper triangular matrix is same as finding the row echelon form method only. That's all. That is a simple shortcut method only. Now we do the problems of this. Problem number 1. In the LU decomposition, of the matrix two, 2, 4, 9, comma, if the diagonal elements of U are both 1, then lower diagonal entry, lower diagonal entry L22 of L is. It is a previous gate question. Fill in the blank question. What is the name of this method? Is it Doolittle's method or Crowd's method? Depending on the unit lower triangular matrix or unit upper triangular matrix, we have two methods. One is Doolittle's, other one is Crowd's. According to Doolittle's method, in the lower triangular matrix, all the diagonal elements should be 1. According to Crowd's decomposition method, in the upper triangular matrix, diagonal elements should be 1. According to this problem, diagonal elements of U are both 1. That means it is a Crowd's method only. Now to find the one of the element L22 of L, according to our method, we write the matrix equal to L into U and we solve for this L22 only. Later I will show you the shortcut method, that is reduction of, that is echelon form method only. First we do this by our Crowd's method only. Let 2, 2, 4, 9 equal to lower triangular matrix L11, 0, L21, L22 into upper triangular matrix, that to unit upper triangular matrix 1, U12, 0, this is 1. Even though it is asked to one element L22, we require all other elements also, because L22 is the last element in the lower triangular matrix. Indirectly we have to find all. Then 2, 2, 4, 9. On right hand side, find the product of these two matrices only. Row into column. L11 into 1. That is L11. First row, second column. That is L11, U12. Next, second row, first column. L21. Second row, second column. L21 into U12 plus L22. So after finding the product of two matrices on right hand side, we equate these two matrices and we try to write the equations and solve for elements on them, which implies L11 equal to 2. Next, L11 U12 equal to 2. L21 equal to 4. And L21 U12 plus L22 equal to 9. Which implies L11 equal to 2, comma, L11 is already known. Then we write the U12 only. U12 equal to 2 by L11. But L11 is 2, so it is 1. Next, L21 is already known. And we require the L22. L22 equal to 9 minus L21 into U12. This is equal to 9 minus L21. What is L21? 4. 4 into U12 is 1. Therefore, L22 equal to 9 minus 4, 5. This is the element 5. So we are asked to find this L22 only. This is according to Crowd's method. Now without this LU decomposition method, without this method, also we can find this L22 by simple shortcut method. Shortcut method. Consider matrix A, that is 2, 2, 4, 9. Finding the L22. This L22 belongs to lower triangular matrix. So we try to reduce this matrix A into this lower triangular matrix. To reduce the matrix A into upper triangular matrix, we apply the row operations, row echelon formula. And to reduce the matrix A into this lower triangular matrix, we should apply the column operations only. That is, we should make the row elements as zeros. We do like this. Here the operation is, our aim is making this element 0 only. Our aim is making this element 0 only. To get this 0 in this lower triangular matrix, we have to make this 0 only. To make this 0, the operation is column operation here. C2 position, C2 minus C1. Now the resulting matrix is, first column is same, 2, 4. Second column will change because C2 minus C1, 2 minus 2, 0, 9 minus 4, 5. Now this is the lower triangular matrix. Here L equal to 2, 0, 4, 5. Now this is the L22. That's all. A simple method. Instead of finding the product of two matrices and instead of equating all these, instead of solving for elements, we can write it like this directly only. So this will be simple for higher order matrices, 3 by 3 matrix. Now we do 3 by 3 matrix only. Problem number 2. Suppose A equal to 3 by 3 matrix, 3, 5, 2, 0, 8, 2, 6, 2, 8. Full stop. If A equal to LU, comma, where L is lower triangular matrix, with diagonal elements as unity, then U and L are. So we are asked to find the two matrices only. Actually, according to one of the method, if you want to find these U and L, we should follow the one of the method. Out of two methods, Doolittle's and Crowd's method, we have to apply the one of the method. But here the particular method depends on the given condition only. Here L is a lower triangular matrix with diagonal elements as unity only. So in the lower triangular matrix, along the diagonal, all the elements should be 1. So this is Doolittle's method, first method only. Now instead of doing this problem by Doolittle's method, we do the same problem in easy way by reducing the matrix in A into upper triangular and lower triangular. That's all. According to row operation, column operations. For upper triangular, only row operations. For lower triangular matrix, column operation. It is a difference only. To reduce the matrix A into upper triangular, row operations. To reduce the matrix A into lower triangular, column operations. Because for upper triangular means we make the column elements as zeros. For making the column elements zeros, we apply row operations only. Okay, let us find the first U matrix. Consider A equal to 3, 5, 2, 0, 8, 2, 6, 2, 8, which implies we reduce the matrix into upper triangular matrix. According to upper triangular matrix, below the diagonal elements should be zeros. That is, first of all, these two should be zeros. We can make these two zeros. It is already 0. We would make it this 0. The operation will be 3, 5, 2, 0, 8, 2. Just we have to make this 0 only. Here operation is R3 position R3 minus 2 times of R1. So not 2, 3 times of R1. 6 minus 6. So this is, wait. R3 minus 2 times of R1. 6 minus 6, 0. 2 minus 10. 2 into 5, 10. 2 minus 10. Minus 8. 8 minus 4. Then 4. First column is completed. Next, we go to second column. Along the second column, below the second element, it should be 0. Which implies A is equivalent to 3, 5, 2, 0, 8, 2, 0. These two are same. So R3 plus R2 directly. Just R3 plus R2. 0, 6. That's all. This is upper triangular matrix. So this is the U matrix completed. Next, we try to find the lower triangular matrix. Consider A equal to 3, 5, 2, 0, 8, 2, 6, 2, 8, which implies A is equivalent to get the lower triangular matrix, along the first row, we have to make these two elements as zeros, these two as zeros. Along the first row, we have to make these two zeros. For making the row elements as zeros, apply the column operations. Apply the column operations. For making the column elements as zeros, apply the row operations. So for getting the lower triangular matrix, we need to apply the column operations. So first column is same. That is 3, 0, 6. First column is same. Next, second column. C2 position to make this 0. 3 C2 minus 5 C1. Next, C3 position. 3 C3 minus 2 C1. Okay. Now 5 into 3, 15. 3 into 5, 15. 15 minus 15, 0. Next, 3 into 8, 24 minus 0, 24. 3 to 6, 6 minus 30. 3 to 6, 6 minus 30. 6 minus 30 minus 24. Next, C3. 3 into C3, that is 6, 6, 24 minus 2 into C1, 6, 0, 12. 6 minus 6, 0. 6 minus 0, 6. 24 minus 12, 12. Which implies A is equivalent to 3, 0, 6, 0, 0. First row is complete. Next, we go to second row. Along the second row, after second element, it should be 0 only. It should be 0. This should be 0. For making the second column, that is for making this element as 0, we use this element only. Use this column. For making this third column element as 0, this third column, along this third column, to make this 0, we use this 24 minus 24. Now the operation is C3 position. This is 6, this is 24. To get 24 here, multiply 4. 4 C3 minus C2. 24 minus 24, 0. Next, 48. 4 into 12, 48. 48 minus plus 24. So 2. Now this is lower triangular matrix, but we require the unit lower triangular matrix. To get unit lower triangular matrix, again we apply the operation. Along the diagonal, we require the 1, 1, 1. For this, we do like this. A is equivalent to C1 position, C1 by 3. C2 position, C2 column divided by 24. C3 position, C3 divided by 72. Now divide the first column with 3, divide the second column with 24, divide the last column with 72. Then along the diagonal we get 1, 1, 1, 1 only. If you divide the first column with 3, then this is 1, 0, 6 by 3, 2, 0, 1, minus 1, 0, 0, 1. This is L. Therefore, U equal to 352082006 and L equal to 1, 0, 0, 0, 1, 0, 2 minus 1, 1. Like this, we can find the lower and upper triangular matrices. It is a simple method to reduce the matrix or to find the lower triangular, upper triangular matrix without using the LU decomposition, Doolittle's and Crowd's method only. If you want to find the L and U according to this method, we can do like this only for 3 by 3 also, or we can follow this simple method only. So with this, LU decomposition is also completed only. LU decomposition is completed, then all the subtopics in the linear algebra are completed only. With this, linear algebra topic is completed. With this, I stop the class. From the linear algebra topic, you will find only simple questions, but the thing is, you require only practice only. Practice more and more problems only. You will be given 3 booklets for this, volume 1, volume 2, and previous GATE solutions booklet. These 3 booklets are more than sufficient for GATE point of view. Just practice all these questions and repeat many times only. Even if you solve only 1000 problems, repeat many times only. If you repeat many times, then we can answer more questions only. If you solve 1 lakh problem and if you do not repeat, no use. Even if you solve few problems, if you repeat many different model problems, then that's enough only. So only the practice is important. Right? Now with this, we stop here. And if anybody has doubt, then can ask the doubt only. Class is completed. Next, we start the doubt session. Hello. 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 Hello.
Hello, sir.
Tell me.
Am I audible, sir?
Yeah.
Sir, can you just show slide number 73, sir?
73.
Sir, can you please explain point number 5?
Point number 5.
Yeah, sir.
For real symmetric matrix, suppose if you take the 2 by 2 matrix, this 2 by 2 matrix. For this 2 by 2 matrix, you will get 2 eigenvalues. For each eigenvalue, we can find the eigenvector. So if you find the eigenvectors are orthogonal vectors only. Here we got only 2 eigenvectors. Between these two, dot product should be 0 only. If you find the dot product of these two, dot product is 0 only. Suppose if it is 3 by 3 matrix, we get 3 vectors, 3 eigenvectors only. Among the 3 eigenvectors, we can write the 3 pairs. Suppose eigenvectors are x1, x2, x3. Then 3 eigenvectors are pairwise orthogonal, means x1 dot x2 equal to 0, x1 dot x3 is 0, x2 dot x3 is 0, always only. That is a guarantee on.
Okay, sir.
Okay.
So one more.
Hello, ask me. Hello, ask your doubt.
Hello, sir. Am I audible?
Yeah, audible.
Sir, can you please explain 83 slide, sir?
83.
Yeah, sir.
This one?
Yeah, sir.
This matrix has 3.
Can you explain just the last point, sir? Just after that, R is equal to rho of A minus lambda.
Yeah. This is having 3 eigenvalues. Out of 3 eigenvalues, 2 eigenvalues are same only. One eigenvalue is different only. Correspond to different eigenvalue, one independent eigenvector exists. That is x1. When eigenvalue is repeated 2 times, corresponding to 2 times repeated eigenvalue, you may get 1 independent or 2 independent only. But either 1 or 2 is given by the formula P equal to n minus r. N is order of the matrix A or number of elements in the eigenvector. For 3 by 3 matrix, eigenvector is of order 3, third order vector contains 3 elements. So n equal to 3. Now we have to find the R. But R is the rank of not matrix A. R is the rank of its characteristic matrix only, A minus lambda. Now to find this rank, we have to consider characteristic matrix like this. And we are finding the number of independent eigenvectors corresponding to 2. That is why we substitute lambda equal to 2 here. For lambda equal to 2, this matrix becomes like this. And this is in echelon form. Rank is 2, which implies the P equal to n minus r. N is 3, R is 2 from this. Then n minus r is 1. That is corresponding to 2 times repeated eigenvalue. The number of independent eigenvectors is only 1. But correspond to 3, 1 more independent. Totally 1 plus 1, the matrix will have 2 linearly independent eigenvectors.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Hello.
Hello.
Hello. Tell me.
Am I audible?
Yeah, you are audible.
So can you show slide number 80? I just want to take a screenshot.
80.
Yes, sir. Okay, sir. Thank you, sir.
Hello.
Hello, sir. Am I audible, sir?
Yeah.
Sir, actually, can you please move to Cayley-Hamilton theorem, sir?
Oh.
Means the introduction. Yeah. Here you said some points, na, sir. Like a square, a cube, a power 4. When are they possible?
Hmm.
Can you please tell the points? Sir?
Oh.
Means like it's like a note point, na, sir. That's why I'm asking.
I will tell you. If A is a square matrix,
Huh.
we write the matrix equation according to Cayley-Hamilton theorem. From that matrix equation, we can find the positive integer powers, a power 2, a power 3, a power 4, and so on. Okay.
Okay.
Suppose the matrix is non-singular, we can find the A inverse. The inverse exists, then we can write a power minus 2, a power minus 3, and so on. So Cayley-Hamilton theorem gives another method to find the positive integer powers of matrix. The Cayley-Hamilton theorem also gives another method to find the inverse of a matrix.
Okay, sir.
Okay.
And that equal to 0, that not equal to 0 is for
Oh.
Singular and non-singular.
That's all. Determinant is not equal to 0. Both powers are positive, possible only, negative and positive only. Suppose determinant of 0, negative powers are not possible.
Both, sir, that not equal to 0 is both possible, and that not equal to 0 means only inverse is possible.
No. Determinant of A equal to 0 means it is singular. If it is singular, A inverse does not exist. A inverse does not exist, negative powers are not possible.
Yes, sir.
Determinant not equal to 0, A inverse exists.
Yes, sir.
That is why for non-singular, all powers are possible. For singular, only positive powers.
Okay, sir. Okay, sir. And now I got it. Sir, can you please move to this problem, sir? Like B equal to 2i, that
Which
lambda cube minus lambda square minus 4 lambda plus 4.
Okay.
They asked to find that of B.
Right, I got it.
Yes, sir. No, not that.
That is in Cayley-Hamilton theorem.
Yeah. Can I tell it?
This one.
Yes, sir. So what if here at equation 1, what if both are different, sir? Like a cube minus a square minus 4a, that one, and here a cube minus a square minus 4a. What if they both are different?
No. Actually,
what would happen?
We are asked to find the determinant of B.
Yes, sir.
If you know the elements of B, we can write the determinant value directly.
Yes, sir.
But elements of B are not given. Instead of given the elements of B, B is given in terms of matrix.
A.
That some matrix. That matrix is in terms of A.
Yes, sir.
So one method is if you substitute I, A square, A cube, we can get elements. Then we can add the determinant of B also. But if you find all the powers and if you find the elements of B, it takes more time on. That is why we never find the like this. We try to get the eigenvalues of this big matrix B. To get the eigenvalues of big matrix, we require eigenvalues of A only.
A.
To get the eigenvalues of A, we are writing the characteristic equation. After writing the characteristic equation, before solving the equation, if you observe the terms in the characteristic equation and the terms in the required matrix B, almost both are same.
Okay.
That is why we are not going to solve the equation.
Okay.
Directly, we are using this matrix equation for simplifying this B matrix only.
Yeah, I understood. So, what I mean is they will get this second statement here. Lambda cube minus lambda square minus 4 lambda plus 4. That one, what my question is, both will get equal only. If at all they both are different, then we need to conclude that we did a mistake somewhere.
Right.
Okay. So one more clarification. Trace of A means just adding of diagonal elements in the matrix.
Correct. In
Okay,
the
sir.
square matrix, some of the diagonal elements is trace.
Okay, sir. Only for square matrix.
Only for square matrix.
Okay, sir. Thank you, sir. Sir, can I have your contact number, sir? If at all, if we have doubts, we can send you in the Telegram.
9848
Yes, sir.
90
984.
9848 905004. It is a WhatsApp number.
Okay, sir. You're good. Sir.
Ravinder Reddy.
Okay, sir. Thank you, sir.
Oh.
Thank you, sir.
Hello. 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 Hello.
Hello, sir. Good evening, sir.
Good evening.
Hello.
You are audible.
Sir, could you please open the 46, frame number 46, sir? Okay, sir. Wait. I can take a snapshot, sir. Okay, thank you, sir.
Hello.
Hello, sir. I'm audible, sir.
Yeah, you are audible. You can ask.
Sir, I had missed this class for 10 minutes, first 10 minutes. Can you please move to the first slide, sir? I will take screenshots.
Today's class.
Today's class, sir.
This one.
Sir, next. The next. The next. Sir, next. Okay, sir. Thank you, sir.
Okay. Hello.
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 Good evening, sir.
Good evening. Ask.
In the slide number 87, Cayley-Hamilton theorem.
87.
Sir, I didn't get how the coefficient of I is 4. Means in the second line of the solution, how to get minus 4 from the determinant or matrix A.
Now, according to our shortcut formula of characteristic equation of 3 by 3 matrix, the equation is lambda cube minus trace. That is sum of the diagonal elements into lambda square plus 2 by 2 matrix determinant, 2 by 2 matrix determinant, corner elements determinant, that is coefficient of lambda minus determinant of A. Here determinant is, if you expand the determinant of this matrix, we get the minus 4. Minus plus 4. This is a characteristic equation.
Okay.
From this characteristic equation, we are writing the matrix equation according to Cayley-Hamilton theorem only. Just by replacing lambda with A. So lambda cube A cube, lambda square A square, lambda A.
Yeah, that I got it. At the in the start, I missed the class, so
okay.
I didn't get the point how to calculate the last. Okay,
okay.
Thank you, sir.
Okay, I'm closing the doubt session also.